Hello students, today I will discuss about the use of transient temperature charts for solving the transient heat conduction problems. Previously we used the lumped system analysis when the Biot number is less than 0.1, that is the case of negligible internal temperature gradient. If the internal temperature gradients or a temperature distribution throughout the system, if you consider, then we have to use the transient temperature charts for solving the transient heat conduction problems. For that one, already we know that the slab characteristic length we are going to use. In that, the characteristic length is 2L for the slab and it is R by 2 for the cylinder and R by 3 for the sphere. And Fourier number, it is a measure of rate of heat conduction across the across the length L in volume L3 and rate of heat storage in the volume P. That can be given as the alpha T by LC square, where LC is the characteristic length. And Biot number, it is the ratio of the heat transfer coefficient of the solid surface to the internal conductance of the solids across the length L. That can be given as the HL by K, where L is the characteristic length we are going to use. And by using these two, Biot number and Fourier number, we can find out the temperature distribution as well as the heat conduction through these systems, transient systems, that is slab, cylinder or a sphere. So firstly, for considering that use of transient temperature charts, I am going to use solve some numericals. That is, the first one is that is for the slab. Okay, in that slab we will consider a 5 centimeter thick iron plate with K is equal to 60 watt per meter Kelvin, Cp is equal to 460 joule per kg Kelvin, and joule per kg. Rho is equal to 7850 kg per meter cube, alpha is equal to 1.6 into 10 raised to minus 5 meter square per second, is initially at 225 degrees Celsius. Suddenly both the surfaces are exposed to atmosphere of 25 degrees Celsius with convectivity transfer coefficient H is equal to 500 watt per meter square Kelvin. Calculate first one, the center temperature at T is equal to 2 minutes after the start of cooling. The temperature at a depth of 1 centimeter from the surface, the energy removed from the plate during this period. These three we have to calculate. For calculating that one, we have to write the given data first. That given data already we have taken. Its thickness is 2L and L characteristic length L we will take, that is half of the length, 2.5 centimeter, that is 0.025 meter. And initial temperature here we are going to take as a Ti. In the lumped system analysis we have taken the initial temperature as a T0, but here we are going to take as a Ti as initial temperature. Because of T0 we are going to take as the center temperature. And ambient temperature or the medium temperature is T infinity, that is equal to 25 degrees Celsius. And whatever the time is there, 2 minutes after the start of cooling, we have to find the center temperature. For that T is equal to 120 second. Okay, 60 into 2, 120 second. For that we have to find the Biot number to check whether this is lumped system analysis applicable or not. Okay, HLC by K, 500 into 0.025, that is 500 is H, 0.025 characteristic length, that is L by 2 is L, 2L by 2 is L, and 60K, then 0.208, which is greater than 0.1, then lumped system analysis cannot be applicable. Then we have to go for the use of transient temperature charts. First one, the center temperature at T is equal to 2 minutes after the start of cooling. Then Biot number HL by K, here we have to take HL, this is half of the length we have to take, the total slab length, HL by K, that is a 0.208, already we have calculated. And Fourier number F0 will calculate, that is alpha T by LC square. Alpha is this one, 1.65 into 10 raised to minus 5 meter square per second, 120 second time, and 0.025 characteristic length square. That will give the 3.072. Okay, then here we have to use the chart. The chart is, that is I am using here the Hegde and Niranjan Murthy chart. That Hegde and Niranjan Murthy data handbook. From that the chart I am going to use page number 52 of the Hegde and Niranjan Murthy that data handbook. And there in that A, whatever is there, that A will be the transient. A is the transient heat conduction chart. In that along the x-axis the temperature ratio is given T0 minus T infinity by Ti minus T infinity, where T0 is center temperature, T infinity is ambient temperature, Ti is initial temperature, again this is ambient temperature. Along the x-axis it is a Fourier number alpha T by L square, and on the curve there is 1 by Biot number. Okay, K by HL, that one by Biot number. Already we have calculated this Fourier number and Biot number. 1 by Biot number we have to take. By taking these two we have to use this one by taking that Fourier number and 1 by Biot number. 1 by Biot number 4.81. From that the temperature T0 minus T infinity by Ti minus T infinity is equal to 0.6 we got. Okay, and by simplification T we have to take 2 minutes. For that, this after simplification for the T0 we got this equation, and if you substitute initial temperature we know, ambient temperature we know, by substituting we are going to get temperature as 145 degrees Celsius as the center temperature after 2 minutes. The second one, the temperature at a depth of 1 centimeter from the surface. Here the distance is from the center we have to take that x distance, but here the distance whatever is given from the surface it is. Then to find the x as a distance from the center, here we have to do the some calculation. Here this one is the from the surface, this is given 1 centimeter from the surface, and x we have to find. The total length is L minus of this 1 from the surface length, then it will give the x. That x we have calculated here. L minus of 1 will give the x 1.5 centimeter, therefore it will be 0.015 centimeter. Then x by L ratio, here we need, why we need, I will tell you that one. Okay, x by L ratio we require. For that it will be the x is 0.015 and L is 0.025 centimeter, then it will be 0.6. X by L 0.6 we got. 1 by Biot number already we calculated is a 4.81. Then again if you go for the chart, okay, the chart B here along the x-axis there is a T minus of T infinity by T0 minus T infinity. You got the T is at a particular radius or at particular distance temperature it is. T0 is the center temperature and T infinity is the ambient temperature. 1 by Biot number is along the x-axis, and on the curve it is a x by L ratio. It is a x by L ratio. X by L already we calculated that x is a distance from the center at which the temperature is required. L is the total length of the slab. Okay, that is half of the length of the slab. Then that ratio is 0.6 we got. Then for that 0.6 here 0.5 is there, 0.8 is there. In between that one here we got the somewhere the point, that curve. Okay, if you plot that one, exactly that value we are going to get here. 1 by Biot number is 4.8 something here. The 4.8 we are going to plot here, and 0.6 value here somewhere we will get, and from that we will get the that whatever this temperature ratio is there. That temperature ratio here we have to take that one. The temperature ratio, it is T, that is x by B or T, it is only directly mentioned that as T minus T infinity by T0 minus T infinity is 0.96. Then again this equation if you simplify for the Tx, there is a 0.96 T0 minus T infinity plus up T infinity, it will give the 0.96, 145 minus 25 plus up 25, it will give the 140.2 degrees Celsius as the temperature at a distance of 1 centimeter from the surface. Then third one, energy removed from the plate per meter square during this time. For the particular 2 minutes of time, what will be the energy removed during that time? And for this we are going to use the third curve. Okay, third curve, that is C curve is there. Okay, here the Q by Q0 is the energy removed, this is Q, and this is initial rate of energy removal, the Q0. And along the x-axis it is a Biot number into Biot number square into Fourier number. and along the curve it is a Biot number. Okay, then here we have to find the Biot number square into Fourier number and Biot number. Then we have to plot here to get the Q by Q naught value. Okay, then here from the chart C, there Biot number square into Fourier number. This one we got the 0.133. Then Biot number is 0.208. And for this 0.208 and 0.133, if you plot on the curve, here, okay, that is this is 10 raised to minus 1, this is a 0.1 and this is 0.1 this one. Then here it will be the 1. Okay, it will be 0.133 somewhere here we are going to get, and this is 0.208, this is 0.208, and if you plot here it will be around, we are going to get the 0.627, that value we will see here 0.45 we got here, 0.45. After plotting exactly we are going to get this one 0.45. Then Q will be the 0.45 into Q naught. The 0.45 Q naught will be the rho CPV Ti minus T infinity. This is the energy equation. Rho density, Cp is specific heat, V is the value, Ti is initial temperature, T infinity is the ambient temperature. And by taking all these we can calculate that is this value, that is the rate of heat removal watt. Then heat removal per meter square, it is asked that one, divided by area we have to divide. Then by dividing that we are going to get this value as a 16.25 into 10 raised to 6 joule per meter square. Okay, this is about the slab problem. Then similarly we will go for the another problem, which is the cylinder. That cylinder is an aluminum rod of 5 cm diameter and 1 cm long. At 200 degrees Celsius is suddenly exposed to a convective environment at 70 degrees Celsius. Calculate the temperature at a radius of 1 cm and heat lost per meter of the rod in 1 minute after the cylinder is exposed to the environment. Take rho is equal to 2700 kg per meter cube, Cp 900 joule per kg Kelvin, K 215 watt per meter Kelvin, and alpha 8.5 into 10 raised to minus 5 meter square per second, H 500 watt per meter square Kelvin. Okay, then here for the cylinder diameter is given. Okay, in the Hegde Niranjan Murthy diameter they have mentioned as a B. Notation they have taken as a B. Here I changed that diameter to the B. The notation we can take anyone. If you are referring the Hegde Niranjan Murthy data handbook, then the radius we have to take as the B. Diameter we have to take radius we have to take as the B. Then Ti initial temperature 200 degrees Celsius, T infinity, that is ambient or a medium temperature 70 degrees Celsius. Length is of the cylinder 1 meter. Radius is given. At radius of 1 centimeter we have to find the temperature. This is second letter R we have to take, at which the temperature is required to find. This is the time 1 minute after the start of the cooling. The characteristic length here we have to take. The characteristic length we have to use for finding out the Biot number to check the whether lumped system analysis is applicable or not. But for using in the chart, it is not necessary to take the characteristic length. Okay, that you have to keep in mind, that one. It's very important. While using the charts, we have to use the HB by K only for finding the Biot number. Alpha T by B square for the finding the Fourier number. But for checking only, we have to use the characteristics for the characteristic length for the cylinder and the sphere. That is very important. Okay, here Biot number is 0.029, which is less than 0.1. We can use the here lumped system analysis. But I already told you that one, at a particular radius we cannot find the temperature. Okay, that's why we should go for the temperature charts. Okay, we should go for the temperature charts. The Biot number once again we are calculating. That checking 0.02 we got here for using the chart HB by K, that is HB by K, it is a 0.058. 1 by Biot number is 17.2. Then Fourier number 8.16, that is alpha T by B square. We used alpha T by B square, 8.16 we got the Fourier number. Then by using the first chart for the cylinder, for the long cylinder, using the first chart, along the x-axis it is alpha T by B square. Along the chart 1 by Biot number we have to use. 1 by Biot number is the 17.2, Fourier number 8.16. Okay, 17.2, here the 16 and 18 is there, here between that one 17.2, and Fourier number 8.16, Fourier number 8.16, here we will get, and if you move in the upward direction, here between 16 and 18, here somewhere 2 to 4, 0.22, 0.4, that value we will get, 0.22, 0.4, that is here we got that one 0.35, 0.22, 0.4, I told you that one approximately, here we got exactly 0.35. Okay, by finding that one, the center temperature we have to find. This required to find the temperature at particular radius. Directly we cannot use the second chart, chart B. That's why chart A we have used, find out the center temperature. Okay, then from the chart B we have to find that temperature at a radius of 1 centimeter. To find that one, we need, that is R by B ratio. R by B ratio at that radius. R is at what radius we require a temperature, B is its radius. That 0.4 we got, 1 by Biot number along the x-axis we are going to get. Then along the y-axis we are going to get this one, temperature. T minus of T infinity, T naught minus T infinity. Along the curve R by B is a 0.4 already we got, and this 1 by Biot number, that is a 17.2 something. 1 by Biot number 17.24 already we got that one, and for that 17.4 something, here 17.4, here 10 and 20 is there, here it is 15 and 17.4 something, here the 0.4 is very nearer to the 1. It is not exactly 1, very nearer to the 1. Okay, that 0.99 we got here, 0.99 we got, and 0.99 by that one, T R by B we are going to get R at T only. T naught point, by simplification that equation we are going to get the T R by B, or at T it is at a radius of 1 centimeter, the temperature 115.045 degrees Celsius. Energy removed from the rod during the 1 minute duration. Okay, that third chart we have to use. In that third chart, it is along the x-axis Biot number square into Fourier number. On the curve it is a Biot number. That Biot number square into Fourier number, this we got 0.0275, and Biot number is 0.0581, and then Q by Q naught value we have to get from that, the Q by Q naught value. Okay, here this one we have to take, and a Biot number, the Q by Q naught value, here we got it as a 0.7. 0.7 we got Biot number. Then that 0.7, the Q naught is a rho Cp phi, and Ti minus T infinity is there, and volume for the cylinder is pi r square L. Pi r square L is the volume for the cylinder. By substitution of that one, we got this as a 2700 density, 900 Cp, pi r square L. L is the 1 meter, initial temperature 200, and ambient temperature 70. We got the 434.19 kilojoule per meter length. Then now we will solve the another numerical which is on the sphere. Okay, for that sphere problem, okay, the similar we have to use similar method, but we have to use the chart, different chart for that one. That only the differs. A metallic sphere of radius 10 cm is initially at a uniform temperature of 335 degrees Celsius. It is quenched in water bath at 20 degrees Celsius. With H is equal to 6000 watt per meter square Kelvin, determine the time taken for the center temperature to reach 50 degrees Celsius. Center temperature to reach 50 degrees Celsius, what time is required, that we have to find. Also determine the surface temperature when the center temperature is 50 degrees Celsius. Surface temperature we have to find when the center temperature is 50 degrees Celsius. Take rho is equal to 3000 kg per meter cube, Cp 1000 joule per kg Kelvin, K 20 watt per meter square meter degree Celsius, alpha 6.66 into 10 raised to minus 6 meter square per second. The given data we will write. Okay, all the given data we have to take. Then for that we have to check the whether lumped system analysis is applicable or not. Byte number is HB by K, HB by 2 or 3 by K. This is characteristic length B by 3, R by 3. Okay, here greater than 0.1 or 1 we are going to get, then it's no necessary to use this lumped system analysis. We have to go for the transient temperature charts. And for referring chart we have to use the HB by K as a Biot number. Okay, then Biot number is 3 here. Then Fourier number here we have calculated Fourier number, this one Fourier alpha T by P square. Okay, that value we have to calculate, that is calculated Fourier number. That Fourier number and Biot number, after calculating that one by Biot number is will be the 0.33, and the Fourier number we cannot calculate, the temperature is required. Okay, that only we are going to determine. This ratio we can calculate as the center temperature is also given 50 degrees Celsius. For that we have to use this one, this 50 minus 20 by 335 minus 20, that will use the 0.0952. This is along the y-axis and 1 by Biot number 0.33 along the curve. Then we have to find out the Fourier number from that one. Here I will show you for this sphere. This is per chart we are going to use. This ratio we know, as the center temperature we know. Okay, Ti minus T infinity by T naught minus T infinity. Then by that one we have to find this alpha T by B square we have to find. 1 by Biot number will be along the curve. Then by using that, the whatever the Fourier number is that we got here. Fourier number will be 0.56. And after finding Fourier number we can find out this time. This time we got here 8.4 second. Then surface temperature. Okay, the surface temperature. Surface means it is R is equal to B. The radius at the surface will be R. R is equal to B. Therefore, R by B ratio will be 1. Then Biot number HB by K, that already we determined. For the Biot number of 3, R by B ratio 0.1. For the 1, we have to find this ratio. T R by B minus T infinity by T naught minus T infinity by using the second curve. Okay, here the second curve here, this use R by B is equal to 1. Okay, then 1 by Biot number we have to use, and for that 1 is here, 1 this curve, and 1 by Biot number, 1 by Biot number value will be 1 by Biot number is 0.33. 0.33 by using 0.33, 0.2 is here, 0.3 somewhere here. Okay, then 1 we cut here, 0.3 something we are going to get as a 0.34, we got this ratio. Then simplifying this equation we get this R by B temperature as a 30.2 degrees Celsius. Like this, by using the charts we can find out the temperature charts.